Prova?
Okay. Okay. So, okay. We were speaking about Eulerian description. So the recording is
It's going on from
starting from now.
Yes.
Okay. So I explained you what is the Lagrangian description and how it works. We were speaking about the Eulerian description for fluids. So basically we were saying that we study the evolution of physical quantities on fixed points of a mesh. And I was explaining you the 1D example with the material points and the particle motion and the mesh motion. So at the time instant t, this example, we assume that the mesh node corresponds to the particle, to the material points. But since the mesh is fixed, we are going to study basically, when we use the Eulerian description, the function we are studying in the fixed region, fixed point of the mesh. So this is the Eulerian description for fluids. Okay, now we move to boundary fitted and non-boundary fitted approaches. There is a famous boundary fitted approach that is ALE, that means arbitrary Lagrangian Eulerian, and it was born like in the 70s. So this is basically a combination of Lagrangian and Eulerian descriptions, and the fluid problem is solved on a mesh that deforms around a Lagrangian structure mesh. Okay? With the 1D example, same example as before, material points and mesh nodes correspond in time instant t. Then we have basically that the material points move and the mesh node move accordingly. Okay? The problem is this one. The problem of arbitrary Lagrangian Eulerian description is that at the interface, because the interface of the fluid and the solid match basically, at the interface we can have distortion of the mesh. Okay? And to solve this problem, one of the main features of the method is that at each time instantly you have to create a new mesh. You have to generate a new mesh. Okay? So this is the main drawback of this method, because the generation of a mesh at each time instantly is costly, computationally costly. Non-boundary fitted approaches. There are a lot of examples of non-boundary fitted approaches. And the idea is that basically fluid and solid are discretized with two independent meshes. Okay, we are going to speak about the fictitious domain that was born in the 94, Grovisky. There are level set method, immersed boundary method, IBM. Okay, passed in 2002, then I will tell you some history about the immersed boundary method. We have niche extreme method and the immersed geometric with fluid structure interaction with IGA. Our formulation started with IBM and then moved to the fictitious domain. Okay, the immersed boundary method history. It was introduced by Peskin in the 70s with his PhD thesis in 1972 and with this paper in 1977. The aim of Peskin was to simulate flow pattern around heart valves. Okay, and so he basically invented this method that is a mathematical formulation of the problem, but also a numerical scheme. These are the pictures from his paper of the 77 of the evolution of the heart valve, and basically the numerical scheme was based on finite differences. Then the immersed boundary method was extended by Peskin and McQueen in the 80s to simulate the blood flow in three-dimensional models. And this method was applied to several problems like simulation of flapping flexible filament in flow in stop fields, insect flights, computational model of aquatic animal locomotion. So several applications during the year for the immersed boundary method. And then there is this review article by Peskin on Acta Numerica 2002, the immersed boundary method, where basically he summarized all the main features of the method. The research about our method basically was born in 2003, when Daniele Boffi and Lucia Gastaldi published a paper with the finite element approach to the immersed boundary method. Problem setting of the immersed boundary method. Okay, we have two regions in RD. D can be 2 or 3. The first one is omega Ts, that is the region occupied by the solid at the time instant t, and then we have omega Tf, the region occupied by the fluid at the same time instant. And and then we consider omega, that is the union of these two, omega Ts and omega Tf. And it's like a container and it's independent from time. For the fluid, we choose Eulerian description in omega with variable x, and we are interested in velocity and pressure. For the solid, we have that omega Ts deforms at each time instant t, and in order to represent its evolution, we introduce a solid reference domain we call B with Lagrange description, variable s, with the map x that maps B into omega Ts with this law of motion. And we call then F the deformation gradient. So the deformation, the gradient of x, or the map x, with respect to the Lagrangian variable s. And this is the picture, the same as before. Okay? So this is the simple concept. Fluid model. We consider a viscosity, mu f positive, and a density, rho f. And again, we are interested in velocity that we call uf, and in pressure, Pf. And we need to introduce, to represent the fluid model, basically the Cauchy stress tensor, we call it sigma f. It is minus the pressure times the identity tensor, plus mu f times the symmetric gradient applied to the velocity. And the equation for the fluid model are the incompressible Navier-Stokes equation. So rho f time derivative of uf plus uf dot gradient of uf equal to the divergence of the Cauchy stress tensor, divergence of uf equal to 0 for the incompressibility, and we assume that uf is 0 on the boundary of omega. For the solid model, again we consider viscosity mu s positive and density rho s. The displacement, we are interested in studying the displacement x and the velocity us, and we need to introduce also the artificial pressure ps. And we assume that the solid is viscoelastic, is made of viscoelastic material, so the Cauchy stress tensor for the solid is the sum of two different contributions. The first one, sigma fs, is the viscous part, and it is basically the same as for the fluid, since we have minus the artificial pressure times the tensor plus mu s symmetric gradient of us, where the artificial pressure ps is the distributed Lagrange multiplier we need to enforce the incompressibility condition in the domain omega. And the second part, the second contribution of sigma s is sigma ss, and it takes this form, symmetric gradient, the determinant of the symmetric gradient to the -1 times pf, where p is the Piola-Kirchhoff elasticity stress tensor, and it is such that pf is the derivative with respect to f of a certain function w, and this w is a potential energy. So the equation for the solid are incompressible viscoelastic solid equation plus boundary condition and initial condition. We have rho s, second derivative of x with respect to time, divergence with respect to s because we are in the reference domain d times this sum and this object basically, and divergence of us equal to 0 to enforce incompressibility. The kinematic condition is this equation basically, so the velocity of the solid us has to be is equal to the time derivative of the displacement x for small x equal to capital X applied to s and t. Then I will tell you how to enforce this condition in the fictitious domain case. Now we move to the fictitious domain approach. The formulation of the immersed boundary method, the evolution from the immersed boundary method to the fictitious domain approach has been done in 2015 by Daniele Boffi, Nicola Cavallini, and Lucia Gastaldi. Basically, the idea is to extend the fluid domain also in the part where that is occupied by the solid. So this means that we define the velocity and the pressure, U and P, in the whole omega. So U is equal to UF in omega T F, and US in omega T S, and the same for the pressure P. And now the kinematic condition we saw in the previous slide is a constraint of U, because we have to impose that U in the region occupied by the solid at the time instant t, so omega T S, that is represented represented by x of st, has to be equal to the time derivative of x. Okay, so this is basically also the connection between the Lagrangian description of the solid with the Eulerian description of the fluid. Okay, coupling. We have to couple the behavior of fluid and structure in the region of omega occupied by the structure. In order to do this, we introduce the distributed Lagrange multiplier, and this means that we consider a bilinear form, C, from a functional space lambda times H1 of B. H1 of B is a suitable functional space for the displacement. We have to notice that all the solid variables are defined on B. And this means that all the computation will be done on B. The defining condition of this bilinear form C is that C applied to lambda z equal to 0 for all the lambda in capital lambda implies that z is equal to 0 in B. We have two possible choices for lambda and C. We can take lambda to be the dual space of H1BD, and hence C is the duality pairing. Or alternatively, we can choose lambda to be again H1BD, and C is simply the scalar product in H1 of BD. Using C, we enforce the kinematic condition using the defining property. So basically, the equality between U applied to x equal to the time derivative of x is represented with C of mu of ux minus time derivative of x equal to 0 for the mu in lambda, using the defining condition. And the notation we introduce now is that the difference between rho s and rho f is equal to, we call it delta rho. And this is the formulation of the continuous problem. So basically, the first equation is the variational formulation of the Navier-Stokes equation, okay, with in addition the coupling term. Then we have the second equation, the compressibility condition. The third equation is the equation of the solid we saw before, with in addition a term related to the coupling condition, and then the kinematic condition with the coupling condition, and then initial conditions. And in particular here, A is a scalar product symmetric gradient of U, symmetric gradient of V. B is the Navier trilinear form. Okay, so this is the continuous formulation, and I notice now that if you see here and also here, obviously, we have that C takes as input, you can say, lambda, and V applied to x, because it is important that the coupling condition in omega has to be set in the region occupied by the solid. Okay, so in omega Ts. For this reason, we have the velocity test function combined with the math x. Existence of uniqueness and uniqueness. Boffi and Gastaldi proved in 2020 the existence and the uniqueness of the solution of this problem, but in a particular case where they considered the linearized problem, so they introduced a new variable w, small w, equal to time derivative of x to kill basically the second time derivative we have here. Okay. And they neglect the Navier's term P. I'm going to say nothing about existential uniqueness. 20 pages paper, so too long. Now we move to the time semi-discretization with the backward Euler. So basically we consider an integer n, positive integer n, and we subdivide the time interval 0t in n equal parts, and we use backward finite differences to discretize the time derivatives with this notation, okay? So I think, you know, there is someone that doesn't know. Okay. So the time semi-discretized version of the continuous problem is this one, and I put in magenta 3 terms that are un plus 1, xn plus 1, and xn plus 1, because basically they are a problem, because we are solving, to solve this problem at the time instant t, we need to know un plus 1 and xn plus 1 that we have not computed yet. So instead of using this backward Euler method for the time discretization, we move to a modified backward Euler, where instead of using un plus 1 and xn plus 1, we use un and xn since we have already computed them. Okay, so a small modification to solve this problem, and the important property of these two schemes is that basically they are conditionally stable without any condition on the time to the time step. This is a theorem in this paper. So if we assume that W, that is the potential energy, is a convex function and delta rho is positive, then the following estimate holds true for backward Euler and modified backward Euler. And in particular, we have that E of x is this elastic potential energy. Okay, I will show you the proof. I mean, it's a little bit. We have rho f over 2 delta t, the norm of un plus 1, L2 norm to the square, minus un, L2 norm to the square, plus nu. Nu means nu f in omega tf and nu s in omega ts, times the norm, L2 norm to the square of the symmetric gradient of un plus 1. That we have, then we have the solid part. We can say delta rho over 2 delta t, norm of xn plus 1 minus xn over delta t to the square, L2 norm on B, because we are in the solid. The same with xn minus xn plus minus 1, and then the elastic potential energy contribution. Okay. So unconditional stability proof, part 1. We set V, the velocity test function, to be un plus 1 in the first equation, so in Navier-Stokes, and then we take into account the fact that the divergence of un plus 1 q is equal to 0 for the q, because we are using incompressibility, and b is equal to 0. This is a well-known property of b, and hence we have this first equation. So rho f un plus 1 minus un over delta t, un plus 1, plus a of un plus 1, un plus 1, plus c lambda n plus 1, un plus 1 xn equal to 0. If we rearrange the first term by means of this identity, basically using x to be the norm of un plus 1 to the square and y un to the square, basically we have that then eliminating this, the term corresponding to this object, we obtain this inequality. Okay, it's easy to see. You have something equal to 0, you are more apart. So. And so this is equation 2 that is related only to the fluid part. For the solid, we take y to be xn plus 1 minus xn over delta t in the third equation, the equation of the solid, and we have to remember that f is the symmetric gradient, the deformation gradient, sorry, and we obtain this third equation. So here we have linear terms. So here we have p of fn plus 1 and then fn plus 1 minus fn over delta t. So we need to discuss this term. In order to do this, we introduce another function, calligraphic w, from 0, 1 to r, defined as a calligraphic of w of t is equal to w fn plus t, fn plus 1 minus fn. And this means that if we apply the chain rule, we have that the time derivative, the first derivative of calligraphic W is this object. And using the convexity of W, we have also that calligraphic W is convex. And this means that this holds true. And applying this inequality with some easy manipulation, we get this other term. And basically we are done, because if we take into account in the equation 3, so here in the solid equation, we obtain this object, and summing up with 2 and 4, this one, and using the fact that the fourth equation is the coupling condition, we have the final estimator. This also is. So this is only this proof. Najwa then will do other proofs for me. Is done my work. Now, operator matrix form. So basically, we know we can represent the variational problem. I showed you before with matrix form with the backward Euler and modified backward Euler. This is the simple structure of the problem. So basically, we have here the Navier-Stokes part, then here we have the solid part and the two coupling terms. Okay? Remember this. It's important. Okay, other time advancing schemes were studied by Daniele Boffi, Lucia Gastaldi, and Sebastian Wolf, and they studied the application of backward differentiation formula BDF2 and the Crank-Nicholson scheme with the midpoint or trapezoidal rule, and basically they show that they are unconditionally stable like backward Euler and modified backward Euler. Okay, stationary problem. Now we move to the stationary problem. Basically, the time semi-discretized problem can be seen as a sequence of stationary problems. So basically, at each time step, we are solving a stationary problem. This means that if we call xn x bar, basically, and un u bar, and if we set pf to be kappa gradient with respect to s of x, so we choose a linear model for the solid, basically. We introduce two new bilinear forms, AF and AS. AF, because if you see, is the one related to the fluid, and AS, the one related to the solid, and where constant alpha, beta, gamma can be deduced from the time step and the physical coefficients of our model. Then if we set u to be un plus 1 to be u, pm plus 1 p, xn plus 1 x, lambda n plus 1 lambda, we have the stationary problem. Okay? So, given f and g and d, our aim is to find u and p, x, and lambda, such that these four equations are satisfied. So, basically, we have Navier-Stokes part here, okay, with the coupling condition, all the hyperelasticity equation I showed you before, with the coupling term, and then the coupling condition at the end, okay, with its matrix formulation. This is important because basically all the analysis about our method is done on the stationary problem. Because it's simple, you can, if you choose a simple, if you neglect some terms in AF and the AS, you can choose analytical solution, put them into the equation, and get a right-hand side for the computation and see the convergence, and see some examples. And I put in blue these two terms, that are the coupling term, because after Najwa part, I will explain you how to assemble with finite elements these terms, because basically it involves integration on a mesh, on two non-matching meshes, basically. So, and it is a crucial aspect of the method. And okay, this is the formulation of the stationary problem. Now is Najwa's time.
Maybe it's also a good moment to ask if there is any question.
Yes, exactly.
Okay, if there is no question, I will make a question.
Obviously.
The fact that you are working under the assumption that your elasticity function in the solid W is convex.
Yes.
I know you cannot tell anything about polyconvexity, but are you allowed to say something about quasi-convexity or some other condition that allows you to prove this kind of stability?
Basically, we are using hyperelasticity. Hyperelastic. No, hyperelastic.
But if you go back, you use the convexity, not the polyconvexity.
Yes, I know.
And so it's a particular case of hyperelastic material, which is the one which are convex. But from whole theory, we know that hyperelastic material are described by all the polyconvex.
Yes.
So you're missing a chunk of materials in your proof.
Yes. Okay, this is the analytic part that I don't know. Okay, basically. Yes, this is a simplification of the model because you know they started from the simplest case and they continue to with this one.
Exactly. What is the point in the proof which precisely needs this convexity?
Here.
Okay, and do you have a clue on how you might get away with other tricks? No.
No.
Okay. There is any other question?
About the conditional stability
Mhm.
in that case, okay, at the continuous level, what do you expect? To have something similar but without the extra terms, right? Just the energy should decay, something like that, right?
Yes. In the continuous case, you have a stability estimate with equality to zero because
Without the extra terms here. So this can be seen like a conditional stability in a different energy, a modified energy, right?
Yeah, something like that. Because the point basically is that this unconditional stability with respect to the time step is crucial because there are a lot of
I know. Okay, but it's probably is a modified energy. So it's not the original one, but okay, the unconditional stability you get is.
No, but also in the continuous case we use this.
Okay. Yeah, what I mean is that, okay, the first terms probably is okay. They don't appear in the stability of at the continuous level. Right?
No. You have the time derivative of u. Yes.
Okay.
Okay. Yeah, I got the point now. Yeah.
Thank you.
Other question?
Okay, and it's time for Najwa.
Okay.
Thank you.
Good luck.
Okay, so thank you for Fabio. He already introduced the idea for me, make it easier to explain to you the rest. The rest is inshallah easier, we don't know. So right and left go down and how to go down.
Okay,
This is next.
Okay, yes, next, the previous, and this is the point.
So this is just the stationary problem in front of you, and if we look at this stationary problem, I removed the color now because of the coupling term is Fabio's part, but here I'm going to talk in general. So as you can see in here, this is the stationary problem, and this is the matrix form of it. Looking at the operator matrix form in front of us, I can't see anything like in this way, but with a simple change of some equation orders or terms, we can see clearly that this is a saddle point problem. And we can use all the information and theory about the saddle point problem. So we can see clearly that this is a saddle point problem, and for the saddle point problem, I can refer for this book here for information. We can show that this saddle point problem is stable and has a unique solution if I can show two conditions. The M sub of this bilinear form here is bounded away from zero, and the ellipticity of this term in the kernel of this bilinear form is satisfied, okay? So that means if I write it, so for simplicity, I will write those two bilinear forms. The double face A is the sum of all right terms, and the double face B is the left-hand side of the last equation. Then I can rewrite my problem in this way. And again, we have two conditions to satisfy. The M sub condition is bounded away from zero, the M sub of the double face B term. And then that one is not as tricky as this one. This one here is this inf sub of B of the double face A in the kernel of B, which is this one in here. And this inf sub is not trivial because if you look closely to the to this block in here, this is itself is a saddle point problem. So this is why we call it a nested saddle point problem or two saddle point problem inside of each other. So this is the second saddle point problem. Remember it because we will go back to this one. So in order to find a good discretization for our big FSR problem, we will break it into some pieces and we will take this piece, the small piece in here, this part, aside, study it, find the stable finite elements for that one, and then use it for the big problem. So this is what we will do. So we will look deeper into the block, the upper left block. And if you look closely, the AF operator in here is the operator associated with a small AF in here, which is nothing but the scalar product plus also the L2 scalar product of the gradient. And the AS here is in the solid region, and it's also again the L2 scalar product plus the L2 scalar product of the gradient. So we can simplify, and the C are the coupling terms. So we can simplify this problem into elliptic interface problem. So this is what we will do. We will go into an elliptic interface problem. We will study its stability in the continuous level and the discrete level, find stable finite element in order to use it for the FSI problem. So what is the elliptic interface problem that we are interested in? Here you can see the governing equation is the Poisson problem with two coefficients beta 1 and beta 2. Those represents the stiffness properties of the domains omega 1 and omega 2. And in our case, we choose the case where omega 2 is immersed in omega 1. We have continuity at the interface, however, jump of the normal derivatives there, and this jump is proportional to the jump of the coefficients beta 1 and beta 2. We have a homogeneous Dirichlet boundary condition at the interface, which is just the interface of omega 1, because omega 2 is immersed in it. To move into the fictitious formulation with distributed Lagrange multiplier that Fabio introduced, we extend our domain omega 1, and we call this extension by omega. So this omega 1 will be filling the entire problem setting, including the solid region. Now our problem is contained of two domains, omega and omega 2, that can be considered independent. Accordingly, we extend U1, beta 1, F1, and we call those extensions U, beta, and F, such that U, when restricted to the region omega 1 is U1, and U restricted to omega 2 is U2, beta restricted to omega 1 is beta 1, and F restricted to omega 1 is F1. Then our fictitious formulation with distributed Lagrange multiplier is this problem in here, and this here we choose we have V is H10 of omega, V2 is H1 of omega 2, and we choose lambda to be the dual space. Fabio said there are two cases. Here we're choosing the case where lambda is the dual space of V2. So in blue here is the Poisson part, in red here is the Lagrange part we enforced here to ensure that the solution U, when restricted to omega 2, is equal to the solution U2 in the common region omega 2. So if we look at the operator matrix form, we can see this is clearly very similar to the part that we take away from the FSI problem. Writing this in a bilinear form, I will write the double face A to be the sum of all blue terms, double face C to be the left-hand side of the last equation. Then my problem here is this one in here, where we can see again this is a saddle point problem, and we can use the theory of the saddle point problem to help us study the stability of the problem. The first thing that we will study is the M sub of C is bounded away from 0, and we can write the M sub of C in this way in here, and the proof of this is very direct. So this is the first proof, it's easy, one line, but be tuned because there are more advanced ones later. But the proof of this is very straightforward because we use the definition of the dual norm. So the dual norm is nothing but the supremum of the duality divided by the norm of V2, and definitely the supremum over V2 is less than or equal to the supremum over the kernel VV2. So that's it, we got the first condition. The second condition is the ellipticity of the double face A in the kernel of B. Or we can call it L-Kerr condition. And the kernel of C is the one in here, all VV2, such that the duality mu, maybe I didn't say that before, but this duality is the duality between V2 and its dual space. So mu and V restricted to omega 2 minus V2 equal to 0. And the L-Kerr condition can be stated as following here. The proof of this is not so complicated, so we start with the left-hand side in here, making use of the fact that omega is the union of omega 1 and omega 2, so I'll use that and distribute the coefficients in here. Don't forget that V and V2 belongs to the kernel, that means they're equal in the common region omega 2, so I can just get rid of those two terms in here and have the leftover here is nothing but beta, the L2 norm in omega 1 squared of grad V, plus the L2 plus beta 2 times the L2 norm in omega 2 of grad V2 squared. Now I will choose the minimum of beta 2, and then I will rewrite this term here as the sum of beta 2 divided by 2 twice. Then I can again make use of the fact that V, V2 are equal at the common region omega 2, so replace one of them with V, take it with that one, a union to give you the norm in omega, the union of omega 1 and omega 2. And again, I'm going to use the fact that V2 belongs to the kernel, plus the fact that V is H10 to move from the H1 semi-norm to the L2 norm, and this will end the proof. So we have that the duality, the L2 scalar product in here is bounded by the H1 norm squared. Okay? So that, since we have the M-sub condition satisfied for the continuous problem, the L-Kerr condition is satisfied for the continuous problem, then we have the stability of our continuous problem that can be written as follows. So the correct norms of the solutions are bounded by the L2 norm of the load functions. Let me just remind you that following this in here, that we know that we are considering elliptic interface problem with discontinuous coefficients with Lipschitz interface. So we have this following regularity of our solution. That is U, when in general, U over the whole domain is in HR, where R is between 1 and 3 halves. However, the restricted solutions, U restricted to omega 1 and U restricted to omega 2, which is nothing but U2, is in HS, where S is between 3 halves and 2. This work, or this problem, has been studied before, studied in those two papers here, published in 2014 and 2015, where they use quadrilateral and triangular meshes, two different papers, two different works, and they approximate the solution using stable continuous bilinear forms and continuous linear forms that are Q1, 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 P1, 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 to approximate solutions in VH, which is the discretization spaces of V, V2, and lambda. Later on, in 2021, the continuous problem of the FSI, the stability of the continuous problem was studied in this paper in here. And in 2022, a paper was published to determine the choice of the finite element spaces, which allows for wider range, not same spaces, so allowed for wider range of choices of the discretization. However, all published or all studies are on continuous elements. So, in my part, I will, maybe after the break, not now, I will explain two things. The first is the work here with the collaboration with Pavia and Gestaldi, studying some finite elements with discontinuous Lagrange multiplier, and we will see later why we are interested in discontinuous Lagrange multiplier. And the other work is about a posteriori error estimator. Any questions so far?
Yes, I do have a question.
Yes.
To go back to the revised paper, you said that the regularity of the solution is going to be...
Where exactly I go? The regularity, okay.
Yes.
Here.
Okay, so but the idea is that that you have there depends only on the geometry of your domain, right? This will depend on the coefficient. So it's the one that is given by
This one?
3/2 if you get a spine domain, and depend in domain with corner.
Yes. But we have the elliptic interface, so that's why this is the regularity. If it's not elliptic interface, we will see other.
But yes, there only depends on the geometry. So you can, if you assume the domain is convex, you get full regularity.
Okay. I didn't know.
Is there any other question?
So if not, oops. If not, I will introduce Fabio again to the floor because he will explain to you something about the interface matrix. Interesting.
This is the last part before the break. So basically we finished the introduction about the general setting, the simplified interface problem, these things. Now we go in some, we discuss some particular features of the method. And in my case, we focus now on the interface matrix for FSI problems with fictitious domain approaches. So go back again to the stationary problem. So as I told you before, the coupling terms are represented by these two matrices, I mean a matrix and its transpose. So CF applied to X bar composed with it. Now we consider the finite element discretization of the stationary problem. So basically, for the fluid part, velocity and pressure, we choose Stokes pair VH QH on a mesh TH defined on the container omega. For the solid discretization, we assume that SH, that is the space for the displacement, for the discrete displacement XH, is equal to lambda, capital lambda H, that is the discrete space for the Lagrange multiplier. And we define them on a mesh TH of B, defined on the reference solid domain. We assume that TH and THB are made of triangles. Okay. Remark, this is important. When C is defined as the duality pairing between H1BD and its dual, when we move to the finite element discretization, if we assume, basically we can assume that lambda H is included in L2 of B, and this means that we can replace basically the duality pairing with the inner product in L2B of D. So we have that the discrete level, when C is the duality pairing, C of mu H, YH can be seen as mu H scalar YH. And if C is the scalar product in H1BD, no modification is needed. Okay? Okay. This is the formulation, the mesh of the interface matrix CF. So basically, if we have the L2 scalar product, if we want to compute at the discrete level CH of mu H VH composed with X bar, combined with X bar, we have to integrate over THB, so on the solid reference domain. What? Mu H and VH of X bar. And this can be seen obviously as the sum of the integrals on each single triangle. The same with the scalar product in each one, with in addition the part related to the gradient. Okay, this is. We have a problem. This is the problem, that VH is defined on TH, while mu H is defined on TH of B. And we have also the fact that we have to consider the actual position of the solid body. So we, for this reason, we have VH of X bar. So let us consider this picture. This is a portion of the mesh for the solid domain B, and we in particular consider this element. If we see the marked counterpart of this element, we have this situation where the marked element is immersed in a portion of the fluid fixed mesh. And basically, we have to integrate here, combining basis function defined in this part, okay, no problem, with basis function defined here on this cyan mesh, taking into account the position of the mapped solid with respect to the solid, to the fluid mesh. And in particular, we have also this problem. In yellow, I indicated basically the support of the finite element basis function related to this point. And we can see that basically the support doesn't match with the solid element, okay? So basically, if we usually have that in a single element, the basis function, for example, are linear. In this case, they are piecewise linear in an element, not in the mesh. Okay? And if even worse, if we have, for example, piecewise linear finite element, we will see, then the gradient is piecewise constant. So we have piecewise constant in a single element, not in the mesh. Okay. Okay, we can use two techniques to integrate this geometry. The first one is the assembling with mesh intersection. So this means that we want to implement a composite quadrature rule over the solid element Ts under consideration. This means that we have to partition each Ts into subtriangles, and this new subdivision is basically computed intersecting the mapped element x bar of Ts with the fluid mesh. And then each new triangle T is basically such that we have that x bar of this new T is included in a unique fluid element Tf. Okay, so basically this is the mapped triangle we saw before. We divide it into some purple polygons accordingly to its position with respect to the fluid mesh. And then if those polygons are not already triangles, we have to retriangulate them, basically connecting the barycenter with the vertices. So basically we have this. The integration over Ts is done considering each new triangle, and pay attention, we are on Ts, not in this triangle. So we are integrating in in B, okay, in Ts, accordingly to the decomposition of the mapped triangle. And this is a quadrature rule, and indeed we have that x bar. We have VH of x bar in pk, so in the quadrature points defined on Ts. The second technique is the assembling without mesh intersection. So basically this means easily we integrate directly over Ts. So we compute the quadrature nodes pk in Ts, and then to consider the velocity shape function that are connected, that interact with this element, basically we check where the mapped points x bar of pk are placed in the fluid mesh. Okay, so basically if we have to integrate over Ts with this Gaussian quadrature rule with three nodes, to understand which the velocity function we need, basically we check, okay, this triangle, this point is here, so we use this shape function, etc. So, okay, this is obviously the approach with the intersection is costly with respect to this one, that because there is no, the intersection part is the costly part. So basically we have that the integral over Ts is simply the quadrature rule applied to the points we just computed without any other computations. Okay, now I'll show you a numerical test for comparing these two approaches. So basically we are in a 2D case with a stationary problem. We consider the stationary problem, the usual stationary problem with these choices. So omega is a square minus 2 to the square, b is 0, 1 to the square, and omega s is this square with x bar given by this. AF is only the grad part, and AS again is only the grad part. And then C is the H1 scalar product. Okay, so Najwa was speaking about the L2 case, the duality pairing case. We now focus on the H1 case, and basically we choose this solution, and then we put them in the equation, and we compute the right hand sides accordingly. Okay, the finite elements spaces. So basically, the fluid variables, we know we need to use a Stokes pair. We choose this one, the Bercovier-Pirenne element, that is P1 iso P2 P1, and its enhanced version P1 iso P2 P1 plus P0. So P1 iso P2 is for the velocity, P1 and P1 plus P0 for the pressure. Okay, why P1 iso P2? Okay, basically we know the most common Stokes pair is Taylor. Okay, so P2 P1, and we know that the P2 element has 6 degrees of freedom, that 3 vertices and 3 midpoints. Basically, the P1 iso P2 has the same number of degrees of freedom. We need to use the same number of degrees of freedom, and this means that basically we have to work with 2 meshes, because the P1 iso P2, instead of using quadratic finite element, we use linear finite element. So VH is piecewise linear on a mesh that we call TH half, because basically QH or QH plus enhanced are defined on a mesh TH, and each pressure element is divided into 4 elements connecting the midpoints. Okay. And QH enhanced version means that the pressure has a linear part plus a constant part. Okay. This is, it's usually in fluid structure interaction there are discontinuous pressures. So for the solid variables we use piecewise linear elements. Okay, so SH and lambda H are simply piecewise linear on a mesh TH40. Quadrature rules for the interface matrix, we use Gauss rules of order 2 and 3. And, and in particular, we will see that when we don't use the mesh intersection, when we don't compute the mesh intersection, if we increase the order of the quadrature, the method doesn't work well, basically. So this is basically the mesh configuration and degrees of freedom of the sequence of tests. So basically, we have this square in its actual position with respect to the fluid mesh, and these are the degrees of freedom for each variable. Okay, and we check the convergence in both cases when we use P1 iso P2 P1 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 and P1 iso P2 P1 plus P0 P1 P1. Okay, convergence plot for the classical Bercovier-Pirenne case. So we have pressure, velocity in L2 and H1, displacement in L2 and H1 norm, and the same for lambda. So we can see, for example, we start from the pressure. The continuous lines are is the convergence line for the case with mesh intersection. So we can see that only if we use the mesh intersection we reach basically the optimal convergence, that in the case of our finite element spaces, they are a low order choice. So basically Taylor is order 2 finite element, P1 iso P2, you don't use quadratic shape function, but you pay in convergence of one order, so you have one order 1 basically. So we can see basically, so here, this is there is also the fact that when you use classical Bercovier-Pirenne element, the pressure has a superconvergence to 1.5 basically. So this is the case for the intersection case, but not for the non-intersection case. The same for the velocity. You can see here it's clear. It's less clear for the H1 norm. Then the same for x. We can see only the continuous, so the method with intersection works well. And the same with lambda. Okay. So, and if we use P1 plus P0 for the pressure, we get something better, in particular for the pressure. Okay, because basically they are almost the same. Other thing, when we use P1 plus P0 for the pressure, the convergence rate is 1. Okay, we don't have superconvergence. But for U, X, and lambda, the method doesn't converge with the optimal rate. Okay, so this is the idea. And for us, it's break time.
Is there any questions? Okay, if not, I have a couple of questions, which are on the Berkovich-Rano.
Yeah.
You are one of the experts of the one of the few experts of the Berkovich-Rano.
Yes, because, okay, no, I don't think. What shall I ask for?
No, not good. Anyway, so the first question is, the first is a remark, since you mentioned the 1.5.
Yes, yeah.
On the, this is actually not, so there are some numerical investigation
yes,
by Boffi and which show this numerically, but...
no, Boffi showed it for mini element.
Yes, for mini, but yeah, you're right, for mini. But on Kamawa, last year came out a paper which proved that this is not true.
For mini, not
for mini, this asymptotically will not hold. Do you think the same reasoning that has been proved in the same paper, which proves that asymptotically this for the mini doesn't hold, will tell you that this is just a pre-asymptotic superconvergence that get into the asymptotic?
I don't know. I mean, we should try to go
mimic that paper.
Yes. No, I mean, yes, to do some numerical tests with very fine mesh and see what happens. I don't know. I've always seen this superconvergence for the everyone. We don't know also why we have this superconvergence only when constants are not used, because when we use P1 plus P0, we have the classical order 1 convergence for the pressure.
The second thing exactly comes when you apply the constant. So I don't remember exactly the definition of the P1 is P2, but the P1 mesh, you take it on the finer mesh of the P1, right? You don't take it on the macro mesh of the
you have the macro element for the pressure, okay?
I use the macro element.
You use the macro element for the pressure.
So this is not so the divergence-free constraint.
So basically. This is a pressure element, okay? So we have the 3 degrees of freedom for the pressure. Since for the velocity we need 6 degrees of freedom, basically we have a submesh for the velocity.
Okay. But then, so the addition of the P0 bubble doesn't make the divergence constraint exact, approximated exact. So because usually you add a P0, you add some sort of it's not a bubble, sorry, the P0 element.
You put it in the big.
In the big, so it's
yes.
not the divergence constraint remains not approximated exactly, because if you put it on the finer mesh, you get that the divergence constraint is approximated exactly.
Yes.
So it's not for the divergence constraint at the solid that you put this. Why do you put the P0?
No, you put the P0 because Boffi, Gardini, Gastaldi, Boffi, Cavallini, Gastaldi, Gardini proved basically that if you use the constants for the pressure, if you add the constants in the pressure, you have local mass conservation, okay. And you have the divergence preconditional on each locally.
Yeah.
Okay.
Yeah.
In the pressure element.
then you wouldn't have this with a
sorry,
Hood-Taylor approximation. You would also have this with a Hood-Taylor approximation locally.
With the constants, not without.
But
Because the same enhanced element has been proposed for the classical Taylor P2P1.
And instead, if you use the Scott-Vogelius, you get away with a full mass conservation because the Lagrange constraint.
I never did that.
Very good. Okay, so if there is no other question, there is any other question, please.
About this stationary problem, what method do you use to solve it?
Sorry?
What method do you use to solve it?
For the linear system?
Yes.
GMRS with PC.
So we use a multi-grid preconditioner from Hypre because this speeds up things quite a bit, and the GMRS is the type of method. Or CG. No, what is CG? I don't remember. I need to check. But
No, we have both, and I use the GMRS.
The GMRS. Yes. But here the preconditioning becomes of key importance.
And we will see, so spoilers for the next part. Najwa will speak about posteriori error estimates and the new elements for the interface problem, in particular for the distributed Lagrange multiplier. And then in the last part, in the last half an hour, 20 minutes, I will show you some computation with preconditioners, some simulation done some clusters in Italy and Saudi Arabia.
Okay, so before we let you go to the coffee break, just one reminder, which is the fact that we will distribute the exit, the coin to get the coffee. Just one thing, if you haven't used yours yesterday night, can you please return it to us? That would be great. Thank you very much. And thanks again. Okay, so I think we can start with the second part of our main class, and I guess now it's Najwa's time to start, so I leave you to her.
Thank you. So, I will talk about two things just like I told you. So let's start with the first thing. I hope you had a good dinner with a cup of coffee now. Me too. So, where is it? Yes. I will start with this work here with the collaboration with Professor Buffy and Gustadi, which is new unfitted mixed finite element methods for elliptic interface problems. And I hope you remember what we did before, and I said we are interested in finding new stable finite elements for elliptic interface problems with discontinuous Lagrange multiplier. In particular, we are interested in having a piecewise constant Lagrange multiplier. And we're hoping that this could improve the local conservation properties later when we move into the big problem, the F cycle. So again, as a reminder, we have the Poisson problem here with the continuous solutions at the interface with jump of normal derivatives that is proportional to the jump of the coefficients. Homogeneous boundary condition, we extend our domain omega 1 to fill the entire problem sifting. So we have two domains that are independent of each other, omega and omega 2. And we have the solution when restricted to omega 1 is U1 and when restricted to omega 2 is U2. Also, we have the coefficient beta here when restricted to omega 1 is beta 1. And the load function when restricted to omega 1 is F1. And this is our continuous problem. Just like I said before, we have VH10 of omega, we have V2H1 of omega 2, and we choose lambda to be the dual space of V2. And this is our problem in here, where we have the Lagrange multiplier terms were added to enforce the solution when restricted to omega 2 equal to the solution U2. Again, I already showed you that this is stable. First of all, this is the saddle point problem, and it's stable in the continuous level. We showed the implicit condition and the Elker condition. So this is the Elker condition, this is the implicit condition. And therefore, we have the stability of our problem, and there exists a unique unstable solution that satisfies this boundary. Again, we have the regularity of our solution. Remember this because we need this in the proofs. Moving into discretizing of our domains, we have the big domain that is filling the entire problem setting, which is the fictitiously extended domain, and we have the following meshes, tau and tau2, that are quadrilateral in 2 dimensions and hexahedral in 3 dimensions, and they are shaped regular. H is the maximum mesh size of tau, and H2 is the maximum mesh size of tau2. We choose our discrete spaces or finite spaces here, VH, V2H, and lambda H, and in our case all are in L2. Therefore, just like what Fabio said, the duality term, that is the duality between V2 and its dual space in the discrete level, can be evaluated as the L2 scalar product in the immersed domain omega 2. And this is our discrete problem now, where we replace the duality term with the L2 scalar product in omega 2. Then, if I write the bilinear forms, double face A is the sum of all blue terms, and double face C is the left-hand side of the last equation. Then our problem can be written as follows, where this is again a saddle point problem, and also for this I will use the theory of saddle point problem to prove the stability here. So we need to show two conditions. The M sub of C is bounded away from 0, and the ellipticity of A in the kernel of C. Before I do that, let's introduce our new elements that we're proposing in here. I'm proposing 3 finite element spaces. All of them have a common thing, which is piecewise constant Lagrange multiplier. So we have 3 spaces. We have 3 spaces, VH, V2H, and lambda H, and we're approximating the solutions using, in the first case, Q1, P0 element, which means we're approximating solutions in VH and V2H using piecewise bilinear polynomials that is in 2 dimensions, uses 4 degrees of freedom in each element that are located at the vertices of the element. The last space is lambda H, and we're approximating the solution there using piecewise constant Lagrange polynomials, and this uses 1 degree of freedom located in the center of the element. And as obviously, this is discontinuous from one element to another. However, those are continuous. They have this common node at the vertices, so it's connected from one element to another. The second element that I'm proposing is Q1 plus a bubble P0, and here we approximate the solutions in VH just like before. However, for the space V2H, we enrich it with a bubble that uses 1 extra degree of freedom in 2 dimensions located in the center of the element. The last element we're proposing is Q2, P0, where here we are approximating solutions in VH and in V2H using piecewise biquadratic polynomials, and this in 2 dimensions use much more degrees of freedom, 9 degrees of freedom in here. There are 4 extra degrees of freedom located in the middle of each edge in 2 dimensions, and 1 extra degree of freedom located in the center of the element. Since this element is using more degrees of freedom, so definitely this is computationally more expensive, but we are expecting that it behaves better. Starting with the 2 conditions, let's start with the proof of the Elker condition. So this is the Elker condition in here. This is the kernel of C. And in this paper in here, we prove that this Elker condition is satisfied under the constraint that beta 2 is strictly greater than beta, and both are positive in the common region omega 2. However, there are some numerical evidence that this constraint can be relaxed a bit, and we see this in the numerical section later. The proof of this is not so complicated. So again, we start with the left-hand side in here. However, here we cannot use the fact that omega is the union of omega 1 and omega 2, because this is not useful in here, because we have, even though VH and V2H belong to the kernel, they're not exactly equal, they're just almost equal, not exactly equal, so there is nothing to cancel in here, so I'm not going to use that. Instead, here comes the constraint. Beta 2 minus beta should be strictly greater than 0, and we will bind it with a eta naught here, a positive number. Since V is in H10 of omega, I can apply the Poincare inequality for this term in here, and this is what I did. We're neglecting the fact that constants can change here. The constants, I'll keep them the same throughout this presentation, but you know, the can change from one step to another. The problem here is how to bound this one, because we know V2H is in H1 of omega 2. So we cannot apply Poincare inequality directly. So the goal now is to bound this term in here, this right-hand side in here, with the norm of L2 norm of V2H squared. In order to use the Poincare inequality, I will rewrite V2H using the mean value. Here, don't mix up with the notation of Fabio, because here E is the mean value of V2H, so I will rewrite it as the mean value plus whatever left of V2H. Then we have that the L2 norm of the left-hand side using triangular inequality is the L2 norm of the first term plus the L2 norm of the second term. And for this red term in here, we can apply the Poincare inequality now, and we get this term here. So what is left? What is left is this blue term in here, and I would love to have here the L2 norm of VH, not V2H, VH, okay? So we will do that now. Making use of the fact that VH and V2H are in the kernel, that means the L2 scalar product of mu H and the difference between VH restricted to omega 2 and V2H in omega 2 vanishes. So making use of that, I will add and subtract the mean value to both sides here. I add it to both sides. And then make the choice of mu H to be the mean value of V2H. Then I can rewrite this as follows, where this term definitely vanishes because EV2H is the mean value. So we're left with that using, writing this in the norm form. So the L2 norm squared is less than or equal to the L2 norm of the first one times the L2 norm of the second one. Divide by this norm, you get this bound. So we got the bound that we want. Just put things together, you get the Elker condition satisfied. So the Elker condition is satisfied for all three proposed elements, for all three finite element spaces that we're proposing. The second condition is the M-sub condition, and we proved that the M-sub condition is satisfied for element 2 and element 3. Reminder, element 2 is Q1, Q1 plus a bubble, P0. Element 3 is Q2, Q2, P0. So we need the bubble part. In Q2 it's already in the element, and in Q1 and the element 2 we add it to the element. And we showed that this is satisfied for those two elements. However, we have also some numerical tests that shows that element 1, which is Q1, Q1, P0, is also passing the M-sub test. Starting with the proof, we see that this supremum over the pairing H and V2H is greater than the supremum over V2H. So if we can find this bound in here, that means the M-sub is satisfied. We will do that. So we will take the singular part. So we will do that by finding or building a Fortin operator by using the Fortin trick. But Fortin operator is a linear operator that satisfies this blue condition in here, the H1 norm of pi HV2 is bounded by the H1 norm of V2, and then the red condition in here, which is the L2 scalar product of mu H and V2 minus phi H of V2 equal to 0 for every mu H in lambda H. We will build our Fortin operator as a linear combination of two other operators, pi 1 and pi 2, in this way, where pi 1 we choose it to be the Clement operator that maps V2 into the Q1 part of V2H. And definitely Clement operator satisfies this bounded here. The second operator, pi 2, we choose it such that it maps V2 into the bubble part of V2H, and it vanishes at the boundaries of the element. And we choose it such that it satisfies that the integral locally over each element of pi 2 V2 equal to the integral of V2 there. So it's just like the pi 2 is just like a bubble, and we choose the height of the bubble according such that it satisfies this in here. Before I start the proof, we need some tools, some pre-proof things. Not only we want that the integral of pi 2 V2 equal to the integral of V2 locally, but also in the reference, we want that to be satisfied. So in order to show this, it's one-line proof. So the integral of pi 2 v2 hat mapped to the physical element, you pay a measure of k2, and then this is by definition of pi 2 equal to the integral of v2. Mapping back to the reference, we gain a measure of k2 that cancels this one, so we get that property satisfied also in the reference. The other thing we need is that this is a norm, and it's a norm in this specific case since pi 2 v2 is nothing but a bubble. So this term equal to 0 only if and only if pi 2 v2 is exactly 0. So this is a norm, and we will use it in the proof. Starting with the simplest one, the red part, even though it's the second condition, but I will start with the simpler one. We have, this is nothing but that, so just take this to the other side. So mu h v2 minus pi h v2, rewriting this using the definition of the linear combination of pi 1 and pi 2. How did we choose pi h? So this is this. For simple notation, we write w for v2 minus pi 1 v2. So we have mu h and w minus pi 2 of w. And by definition of w, if you remember, first of all, if you remember that mu h is a piecewise constant. So locally in each element, it's 1 in one element, 0 in the other elements, right? The basis functions are 1. So locally, this is nothing but the integral of w equal to the integral of pi 2 omega, which is by definition of pi 2. So this is equal to 0, and then therefore the pi h satisfies the second condition of the 410 operator. That was the easy one. So let's see the second one, which is the first condition. The first condition, we want to prove that the h1 norm of pi h v2 is bounded by the h1 norm of v2, using the definition of pi h as a linear combination of pi 1 and pi 2, and triangular inequality. We have two pieces. The first piece is very trivial and direct, because by definition of pi 1, it's a Clement operator, so it directly satisfies this. So what we need to prove that this bronze part in here is bounded by the h1 norm of v2. Again, we will write w for short notation. So we have that the h1 semi-norm of pi 2 omega is, when you write it, when you map the norm to the reference element, we we pay h to the minus 1 here, and we gain a square root of measure of k2. And then in the finite dimensional spaces, norms are equivalent, so this is equivalent to this norm that we showed in the beginning, it's a norm. And by definition of pi 2 omega hat is, the integral of pi 2 omega hat is equal to the integral of omega hat. We also showed that in the beginning. So by Cauchy-Schwarz, this is less than or equal to the L2 norm of omega hat, which is mapped to the physical element here. You pay a square root of k2, measure of k2. So those cancel each other, and we're left with this bounding here. By definition, L2 norm, pi 2 omega is vanishing at the boundary of each element, so locally this can satisfy the Poincare inequality, so we will use that and use the bound from here. Now we have two pieces. We will glue them together in order to find the h1 norm of pi 2 w, which is nothing but the sum of those two. And this is w, if you remember, it's v2 minus pi 1 v2. Which is pi 1 is the Clement operator. So by Clement operator, Clement operator satisfies this bound in here, that the sum of h to the minus 2 L2 norm of v2 minus pi 1 v2 squared is less than or equal to the h1 norm of v2 squared. So we have all the pieces we want. This term by Poincare inequality, we said in the beginning, is bounded by the h1 v2, and this one is in here bounded by the h1 norm of v2, so the sum of them is also bounded by the same norm. Therefore, we have the first condition satisfied for the 410 operator. So we have a 410 operator that is, that is h1 stable, and therefore the discrete and subcondition is satisfied for the two elements that I said in the beginning, only element 2 and element 3. Element 1 we didn't prove yet. Actually, we don't have the proof, the theoretical proof, but we have a numerical results. So Since the L suit satisfied and the L condition is satisfied for both element 2 and element 3, then I can go ahead and write the stability or the error estimate. Here we have to have tau 2 to be quasi-uniform because we use some inverse inequality in the proof, but for tau 1, for tau we don't need that. So this is the error estimate, and we showed that this h bar is the maximum of h to the r minus 1. H is the maximum mesh size of tau, and h2 to the 1 minus t, where t is between half and 1. Starting from here, again we go back to the same book, same reference of everything. We have that the error is bounded by the best approximations, like we wrote here. And by using the regularity assumptions of u and u2, we can bound the infimum of the u minus v for every v in vh is less than or equal to h to the r minus 1 times the r semi-norm of u, where r is between 1 and 3 halves. The second one, also here we use the regularity assumptions on u2, so we have this is bounded by h2 to the s minus 1 s semi-norm of u2, where s is between 3 halves and 2. However, it's not as easy to find the bound for lambda minus lambda h hat. It's not as easy to find what is the infimum of lambda minus mu, which we will show now, but it's a little bit longer, it's not like linear. So let's make use of the characterization of lambda. This characterization in here is obtained from the problem itself. So just like a symbol playing with a problem, you get this characterization of lambda, which is the duality between lambda and v2 equal to some integral over omega 2 of this thing in here, plus some integral at the interface of this. We will write our lambda as sum of two lambdas, lambda 1 and lambda 2, where the duality lambda 1 and v2 is nothing but the first integral, and I will show you later that this blue term in here satisfies that this lambda 1 minus some lambda 1 h that I will show later is less than or equal to ch2 times the L2 norm of this in here. The second part is satisfying that the duality between lambda 2 and v2 is the integral over the interface, the second term in here. And I will prove in 2 steps that lambda and v2 minus v2h is bounded by this with an s power, and lambda 2h and v2 minus v2h is bounded by this with the 1 minus t power. And 1 minus t is dominating in here, so we will end up by having this bound in here, and we will see this in steps. So we have a blue part and a bronze part. I don't know, it's looking like it's red, but don't know what do you see from there. So let's start with the blue part. This is the duality between lambda 1 and v2. As you can see here, maybe it's clear that from the definition of the problem, if you remember, that f is an L2 of omega, and f2 is an L2 of omega 2. B and beta and beta 2 are in L infinity, and beta 2 is bounded away from 0. So that means this whole thing is in L2, which makes v2 in L2, which makes lambda 1 in L2, in the dual space of L2, which is L2. So that means that we can easily find that the norm or L2 norm of lambda 1 is bounded by the L2 norm of beta divided by beta 2 times f2 minus f. Now we want to find the best approximation of lambda 1. We want to find lambda 1h that best approximate lambda 1. We will define some projection here, L2 projection that maps something in L2 into the dual, into lambda h. And we choose our lambda 1h to be the projection of lambda 1. Obviously, lambda 1 minus lambda 1h and mu h is 0. So we have this norm in here, in the dual norm of lambda minus lambda 1h is the supremum of lambda minus lambda 1h and v2 divided by h1 norm of v2. Again, this is in the discrete level, so we can, okay, this is L2. This is L2 again, so all L2, so we can replace with the L2 scalar product. And we notice that also here we can subtract from here using that. We're subtracting the projection of V2, which is in lambda h. So we end up by having the L2 scalar product of lambda 1 and V2 minus the projection of V2. which is bounded by the L2 scalar product of the first part, of the first here, and times the L2 scalar product of the second argument. Okay, so this one in here is obvious, I think. This is bounded by H2 times the H1 norm of V2. This one we already found before. It's bounded by the L2 norm of this quantity. So I did that. So that was the I will start with the easier. So that was the easier. Now the more complicated part is the next one, because here we have lambda 2 is not in L2. And we will see. So we have U from the regularity assumptions of U. It's in HS where S is between 3/2 and 2. That means the trace of the normal derivative grad U2 belongs to H to the S minus 3/2 at the interface. That makes lambda 2 in H minus T, where T is between 1/2 and 1. Okay? So the first tool I need is the H minus T norm of lambda 2. Using the definition of the dual norm, this is the supreme of the duality divided by the HT norm of V2. By definition of the duality from here, remember that we said that what is it? Yes, so that the normal derivative of grad U2 is in HS minus 3/2, so we have those are the HS minus 3/2 norm at the interface of this quantity times the H 3/2 minus S of V2. Now I would love to replace this with HT, so in order to cancel this with that. So I will bound this term with something that is greater than it. So here T minus 1/2 is greater than 3/2 minus S, so I can do that. And then using the trace theorem, we map from interface, we move from interface to the entire domain. So S minus 3/2 will become S. Okay? And then this one in here will become HT. Cool? Those cancel each other, so we get that supremum is no longer needed, and the H minus T norm of lambda 2 is bounded by the HS norm of U2. Let's use it. So let's define lambda 2H to be the same definition with the discrete V2H in here. That makes lambda 2 minus lambda 2H and V2 equal to 0, because here it will be the same definition, but VH minus V2H. So they cancel each other, so this is 0. And then I will rewrite this again, same as before, lambda 2 minus lambda 2H and V2 equal to lambda 2 minus lambda 2H and V2 minus V2H. From here, we can add that. And then separate them lambda 2 and V2 minus V2H minus lambda 2H and V2 minus V2H. Obviously, this one is discrete, so I can replace the duality by the L2 scalar product. I will deal with every one of them alone. So the first one, the duality between lambda 2 and V2 minus V2H is this integral in here, which is bounded again, same argument, by the HS minus 3/2 norm at the interface of the normal derivative of the gradient of U2 and the H 3/2 minus S of V2 minus V2H. Here, this is bounded by, I can use the bound in here, which is, so 3/2 minus S plus S minus 1 is 1/2, so we can do that. And then using the trace theorem, this maps into the H1 norm of V2. Not mapped, moved from interface to the whole domain. And then we have the H2 to the power S minus 1 here for this term. That means, let's take this aside. Let's start with the second one, the L2 scalar product of lambda 2H and V2 minus V2H. This is bounded by the L2 norm of the lambda 2H times the L2 norm of the second part. That means we have the bound of this part in here to be H2 times the H1 norm of V2, and we need to bound this one. I know it's all inside each other, but we're almost there. So let's bound this blue term in here. This is the L2 norm of lambda 2H, which can be defined as the supremum of lambda 2H and V2 divided by the L2 norm of V2. of V2. This is again equal to if I replace lambda 2h with a lambda 2, and then here we're using the lambda 2 is in h minus t, and pi h v2 will be in ht. And what we need now is, okay, so this we found before. This we found in the beginning in red. The first thing we did in this part, which is bounded by the sh norm, hs norm of u2. But this part in here is not there. So what we did is we used the inverse inequality in here, and this is why we have the quasi-uniform condition for the mesh. And this now we need to, okay, so we're almost there. We need to find the supremum there. We need to map, we need to have, let me just go back. We need to have this bounded by the L2 norm of V2 in order to cancel them. So we notice, or if you remember that pi h is the Fortin operator that we built, which is made of linear combination of pi 1 and pi 2. If we replace the pi 1 from Clement interpolation to another quasi-interpolation operator that bounds in L2, we get this bound in here. So we can replace the lambda pi h of V2 by the L2 norm of V2, and they cancel each other. So we have this bound in here. Putting things together, we get that the lambda 2 minus lambda 2h, the dual norm of lambda 2 minus lambda 2h is bounded by h2 to the 1 minus t times the hs norm of u2. Why did I choose 1 minus t? Because we have another bound there. It's, I don't know if you remember. Here we have h2 to the s minus 1. So it's two pieces together, but 1 minus t wins the game here. It's bigger. Okay, so we have that the sum of all the terms is bounded by some h to the power times the r norm of u, s norm, hs norm of u2, and the L2 norm of this quantity, where h bar is the maximum of h to the r minus 1 that come from this term here, and lambda h2 to the 1 minus t, where t is between 1/2 and 1. So that means our stability is proven in here with this one. So we're done with the M-sub condition and the Ilker condition, at least for element 2 and element 3, and the stability also is, for both elements. Just remember that in our case we're using quadrilateral element and hexahedral elements. However, Fabio is using triangular elements, and this all proofs, all results in this work can be extended to triangular or tetrahedral meshes with the corresponding elements in here. So P1 plus some bubble that is different than our bubble, and P0, and P2 plus a bubble P0. Here we're adding a bubble because P2 in a triangle doesn't have the bubble part in the middle. So we have to have that for the proof. And the last one fails to satisfy some necessary condition for the M-sub. The number of degrees of freedom for P1 can be less than P0, so therefore this element is not working. As an example, we have a simple two-dimensional case, 0, 6 interval squared, and exponential 1 to 1 plus pi squared, right-hand side ones, and Dirichlet boundary conditions. I will talk here in the numerical section about three main things: the coupling term, the M-sub test, numerical M-sub test, and then the conversions. Just like what Fabio said, we have to evaluate the L2 scalar product of lambda h and vh restricted to omega 2, which is the integral of some product of basis functions that are in two different meshes. So we have to be careful with dealing with this one. Fabio, in his paper with Pavia and Gastaldi, they proved that the intersection approach is the best to deal with this one. And if you use non-intersection approach, even if you increase the quadrature rule order, you will not achieve the correct conversions, the optimal conversions. So how does we, you remember we have squares meshes. So for simplicity, I will consider tau 2 to be made of only one element. And the idea is to remesh the the solid element, the tau2 into smaller part that intersect with only one element of the background mesh, as you can see in here. This I will call tau2 bar. In our case, tau2 bar is still quadrilateral, so we don't have any problem with remeshing again or all of that, so we will just go ahead with our old code, but with a new mesh. So just again remember that we're using piecewise constant Lagrange multiplier, which means the intersection between the support of phi I and psi j is only one element of the new mesh, which is, for example, this red part in here. So you go and find the correct quadrature rule in your reference element, map them to the correct position in the red element, and find or evaluate your integral. If you're neglecting the idea of the intersection, that means you will map this quadrature point out of the support of the product. Also this one, maybe it's mapped out of the support of the product. Also this one, so you will lose a lot of information. Then the evaluation of the integral is trivial, so we will, since we have piecewise constant Lagrange multiplier, it stands by 1 in one element, 0 in the others. And then we have this result here. So the integral is nothing but the sum of all the quadrature point units and the not basis function. The second thing that I will talk about is the numerical immersed test. And here we use this paper as a reference to rewrite our immersed condition into the eigenvalue equation here, where N1 is the matrix associated with the dual norm, N2 is the matrix associated with the H1 norm of V2, and C2 is the operator associated with this binomial formula here. And we showed that all, here I'm showing also some old work, which is Q1, 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 but all of them, under increasing of refinement of the mesh, are bounded away from 0, therefore all of them passes the immersed test, including the one that we didn't show, which is Q1, Q1, P0. The last thing I'm going to talk about in this part is the convergence. We test this in two cases. Beta 2 is greater than beta, and beta 2 is less than beta. However, for the second case, we're violating the discrete Elker sufficient condition that we said in the proof, right? We test this under different ratio between H and H2, so here we have 5 different ratios: quarter, half, 1, 2, and 4, 8 cycles of refinements, and up to 160,000 elements used. The first column in here is representing the ratio half, the second column represents the ratio 1, the third column represents the ratio 2. First row is Q1, Q1, P0, second row is Q1, Q1 plus a bubble P0, third row is Q2, Q2, P0. This is the first case where we have beta 2 is greater than beta, and in this specific case, beta 2 is 10, beta is 1. And as we can see, even though we have some oscillations because of the fact that we're using unfitted meshes, but all of them are converging with the optimal rate. We notice that as the ratio decreases, we have less oscillations at the end. Increasing beta 2, let beta 2 be 10,000, almost the same results as shown. However, if you see the second case, where we have beta 2 is less than beta, here we let beta to be 10, beta 2 to be 1. At least we can see that Q2, Q2, P0 is optimally convergent. For Q1, Q1 plus a bubble P0, it's converging in the case when the ratio is greater than 1. Q1, Q1, P0 doesn't converge. So this, we increase this more by making beta to be 10,000, but all of them fails to converge. This result of the second case suggests that this constraint of beta 2 minus beta should be strictly positive, can be relaxed a bit, maybe under some conditions on the ratio and how big is the difference between beta and beta 2. That was the talk of the first part. I hope I didn't bore you with a lot of proofs, but second one I promise no proofs. خلاص, we're done. We're done with all proofs. Any questions about this one?
Yeah, so if you can go back to this case that you have defined, right? You said that you have this
Which one?
A couple of slides before. No.
After?
Yeah, when you were discussing the triangular space, the corresponding triangular
Ah,
space,
okay, okay.
you can add a bubble into a
Yes.
triangle. Okay, you're here, right? And in my mind, you can condense that bubble, and then your degree of freedom become much more manageable, right? And then I don't see the advantage of taking a Q2, which has got a bubble inside.
Exactly.
So this.
This is, so if you use Q2 for a square, you have already the bubble inside.
But can you condense that bubble?
What do you mean by condensing?
So can you eliminate the degrees of freedom corresponding
No.
to the bubble?
The problem is we want the bubble for the proof.
Yeah, but you can. So you want the bubble for the proof, but then you don't need the bubble numerically.
So numerically we are. So you thinking that those could work without a bubble?
No, you keep the bubble, but you condense the bubble.
I don't know, maybe.
So you use one. So you don't use the degrees of freedom.
I see your point.
And then you get away with using the same less degrees of freedom because the bubble that you added you can condense. But I'm not sure if you can do the same with a quadrilateral element. So
I don't know. Maybe we should try this. I will see. I don't know. Any other question? Okay. So that means we go to more interesting part. No proofs there. At least nothing that I show, because that work is still under progress. So okay. Yes, here. So this work again is with Professor Pavia and Professor Credali, but still under preparation. It's not 100% finalized. Maybe I get some ideas from you guys. So here we're talking about a posteriori analysis of elliptic interface problems. If you remember our problem, I will rewrite it here using the bilinear form L as the sum of all left-hand side. Then the bilinear form is equal, so my problem is to find U2 lambda in the continuous level. That is L equal to the scalar product FV plus the scalar product F2 minus FV2. We know from the previous work that the M sub is satisfied in the continuous level. In the discrete level, we have the discretization, tau 2, same as before. We have the collections of all edges in tau and tau 2 in here, epsilon 1 and epsilon 2, and we have the maximum mesh size of each element and edge. We have the discrete problem in here where we need to find U2H and lambda H in the discrete spaces such that the LH, the discrete bilinear form equal to F and V, the scalar product FVH plus scalar product F2 minus FV2H. And we know also that this is satisfying the MC condition, at least for theoretically for element 2 and element 3, numerically for element 3. Remember our elements, Q1, Q1, P0, Q1, Q1 plus a bubble, P0, Q2, Q2, P0. The theory of the posteriori analysis is there for a long time, and people are working on different types of posteriori analysis. Some are residual-based estimators, some are numerical basis errors, some are based on the auxiliary local problems. However, for interface problems, this is recently developed, and we have some residual-based estimator for confirming finite elements. This is for interface problems here I'm talking, and some others for discontinuous Galerkin elements for non-confirming finite elements. Some other works are presenting recovery-based estimator for confirming linear finite elements, mixed and non-confirming linear finite elements. However, maybe it's only up to me, up to my knowledge. I don't know. Maybe there is something, but up to me there is nothing for FDDLM approach, a posteriori analysis for fictitious domain formulation with distributed Lagrange multiplier. So this is our novelty in here. We would like to find a good estimator for elliptic interface problem that is in the FDDLM formulation. And we aim to have a better control over the error, better accuracy of our model, and less computational cost. We defined the errors E, E2, epsilon to be the error of U, U2 lambda, and epsilon tilde here to be the error of the extended lambda. We define our sets, omega ki bar to be the set of all elements that share at least one point with the element ki. The element omega ki with no bar, neglecting the elements that only intersect with ki in one point. Same idea for omega ei and omega ei bar. Omega ki is the set of all elements that share one point. We have two tools that are usually used for a posteriori estimate analysis. The first tool is the bubble functions. And we have a bubble function that is an interior bubble function, psi ki, that has a value between 0 and 1, and a support inside the element and satisfy those bounding here. The second bubble function is a bubble function at the edge of the element, which has a support in the two elements that share that edge, and has a value also between 0 and 1. We extend this bubble function, we call the extension psi ei bar, following the level line like this in here. And this satisfies those bounds in here. The second tool we're using is the interpolation operator, and here we're using the Klein interpolation operator that maps sum all the L2 projections of V into the Q1 part of the set of all elements that share one point of the V, with the cell K, or is it K1 here. And then it satisfies those bounds in here locally. The second operator is a Klein operator that also sum all the L2 projection of V2 into the Q1 part of the set, which satisfies also those bounds locally. Then we define our residuals. The main idea of this residual is that it doesn't make use of any information about the continuous or exact solution. We don't know anything about the exact solution. As you can see here, only we're using the discrete solutions. So the first, we have two sets of residuals for each mesh. We have the first mesh, which is the extended mesh, and we define the residual inside the element to be the difference of the discrete solution. So here, the discrete solution of the strong formulation, beta gradient H minus the extended lambda plus the projection of F. And the residual over the edges of this mesh are the jump of the normal derivatives. If that edge is an interior edge, and 0 if it's a boundary, because here we're using only directional boundary. The second element is exactly the same. So the residual inside the elements are just the discrete solutions of the strong formulation, and then the residual over the edges are the jump of the normal derivatives there. Then we define our indicator that will give us a good prediction where is the error is the highest in order to refine more in that case. And the indicators we define for elements in omega and elements in omega 2 are some weighted sum of the norms of the residuals that we defined a minute ago. Then the overall error indicator of the mesh tau will be the sum of all the local indicators. Same for the second mesh. There are some oscillation terms that will appear, and those are some higher order perturbation of the data, or some people call them correction terms. And for short notation, I will write OSC for the oscillation term in K1 and in K2. Then in this, hopefully finished soon, paper, that we proved that the reliability bound, or the global upper bound, that the correct norms of the errors are bounded by the indicators and some higher order perturbation of the data. The local lower bound, or what is known as the efficiency bound, we proved that locally the indicator is bounded by the correct norms of the errors plus some higher order perturbation of the data, where beta bar here is the maximum between beta 2 minus beta and beta. I mean, everyone I think knows how to do the adaptivity, but just a reminder here, we're using solve, mark, refine strategy. So we start by solving in a coarser mesh. We calculate all the local indicators in each element, and then we check the overall indicator. If it's met tolerance, we can break the loop. If not, we have to continue. Then if we're continuing, we will mark all cells with the local indicator that is greater than or equal to some percentage of the overall indicator. This alpha 1 can be anywhere between 0 and 1. So it's just like a percentage of the total indicator. Then if we want to do also coarsening, then we have to mark all cells with a local indicator that is much less than some percentage of the overall indicator. Then mark and coarsen all this marked cells. This will give us a new mesh with finer in some places, coarser in some places, and then you start over. In our case, in 2 dimensions, we split one quadrilateral element into 4 children, and in 3 dimensions, it's split it into 8 children. So you're just connecting the parallel faces from the middle to cut it to the new mesh. Okay, so here we're maybe having a hanging node, maybe. Not sure, no, I'm just joking. So here we're having a hanging node, but we will not have discontinuity in the solution because we are forcing the solution to be continuous by adding some constraint. So there is a matrix before the solution that will force, for example, if you're using linear elements, then you force the solution at node 6 to be the average of the solutions at 9 and 3. So it's like going through, so it's continuous. In our case, we did alpha 1 to be 0.3, and we choose this specifically because, okay, so if you remember, let me just go back, yes, here. So every cell is split into 4. That means if I'm doing a global refinement, I will multiply the number of cells in every cycle by 4. This is a big number. But in our case, if I choose alpha to be exactly 0.3 in 2 dimensions, I will just get 2 times the number of cells in the previous cycle. So this is why we choose this number exactly. In 3 dimensions, you can use 0.7 in order to get double the number of cells. We did 8 cycles. Okay, so this is not what we did more, but let's say that you're doing 8 cycles of refinement and you start in the first cycle with 64 cells. Then you get, you end up by having 3 million cells used if you are doing uniform refinement. However, if you use this adaptive refinement with alpha 1 0.3, you will have only 11,000 cells. We choose in our case alpha 2 to be 0.03, which means we're refining only cells with local indicator less than 3% of the total indicator, which means the error there is not that big, so why are you having extra degrees of freedom? And this will give us less than 2 times the number of elements of the previous cycle. So the difference is not big because this number is not big, but still, you're reducing the 2 into something like 1.8 something. I'm not sure exactly how much, but if you want, we can calculate it. We started with 81 degrees of freedom. So in adaptive refinement, we reach about 60,000 degrees of freedom for 15 cycles. In uniform refinement, we reach up to 4 million degrees of freedom in 8 cycles of refinement. We did 2 tests. The first example is the interval 0, the omega is the interval 0, 3 pi squared, and so it's the square, and omega 2 is the square pi and 2 pi. Okay, so this is the example, and in order to make it simpler, this is the solution. So we have here very clearly jump of the normal derivatives at the interface, and we have some change of the solutions, rapid change of the solutions at the peaks and less as you go down the high. This is 8 cycles of refinement. As you can see clearly, we have extra refinements at the peak, but more refinements at the interface where we have the jump of the normal derivatives. The second example we're solving is this one, which is the same as the one that we did in the previous paper. And this is the exact solutions. And this is 8 cycles of refinement. And you can see clearly we have extra refinement at the interface, less everywhere else. So it's almost the same everywhere else because this solution is not changing a lot, unlike the first example. The This is a 3-dimensional case where this is a slice of a block. Okay, you can see clearly here. I didn't have a zoom on this one, but there is extra refinements at the interface and almost the same everywhere else. Okay, the main idea of the indicator is when you don't have the exact solution. Like we did in the second example, we don't have the exact solution. So, but the first example, we have the exact solution, so let's test our indicator. You can see clearly here in blue, this is the indicator of the first mesh which we call it eta 1. And in red, this is the H1 error of this exact error. So for this example, we have the exact solution. And as you can see that the indicator is bounding the exact error, not only that, but it's also behaving exactly like with the same slope as the exact error. Which means that if we can use this indicator in order to know where is the error bigger, and we find there without knowing the exact solution. However, if you look at the second indicator, we were okay at the beginning, up to some threshold, where the indicator is starting to lose or not following the correct rate of convergence of the exact solution. And we noticed that numerically, if we replace in the definition of the indicator, then this specific indicator, which is eta 2, if we replace the H1 norm with the L2 norm, or with H times the H1 norm, we get a better behavior. But this is still under investigation. So if you have a solution for this, come to me. That's it for this work. If you have any question. Yes.
Okay, just having a question. Coming back to the case of the hanging node.
Hanging node, yes.
Yes, it's 72, I think. No, sorry, 71.
Yeah, sure.
Yeah. Okay, it is true that you can impose the continuity, continuity strongly, right? But you are changing the space because you are this is a fake degree of freedom because you are forcing the value. So on the element at the right, you have something that is not piecewise linear. It's a different space, right?
I'm not sure.
No,
if it's
sorry.
space.
No, it's. I think.
You have the same base function, right? The base function instead of the element are the same. You are refining that the space is still on each element by linear. Let's say you're using the Q1 by linear on each element, and you just add an equation that inputs the continuity and the hanging nodes.
Okay. Thank you.
You're welcome. Any other question? Okay, so thank you for listening to me. That was all of it for me. Now it's time for Fabio for the last part. And we will talk about parallel solvers. Give him a second. Thank you.
Parallel solver for FSI problems. This is a joint work with Daniele Boffi, Lucia Castaldi, and also Simone Scacchi. So basically, we want to study the robustness of our method with respect to the mesh refinement, the strong scalability, time step refinement, and volume loss. We studied basically two-dimensional interaction systems, and we consider both linear and non-linear solid models. And we design a Fortran code combined with PETZ and maps, and we run the simulations on Chain cluster in KAUST, News cluster in Pavia, Galileo, and Marconi in Cineca. Okay, the model problem is the same as before. We dropped out B, and the term with the second time derivative of x, considering the two density to be equal, so rho f equal to rho s. For the distributed Lagrange multiplier, we work with lambda as the dual space of H1, So C is the scalar product in L2 at the discrete level. So in the previous part, I showed some numerical test with the H1 multiplier. Now we work with the L2 scalar product. And for the finite element discretization, now we work with the Q2 element for the velocity, P1 element for the pressure, and SH and lambda H, P1. So here we are using square meshes for both solid and fluid. And we work with the modified backward-Euler as time advances. The assembling of the interface matrix. Okay, so for the assembling without mesh intersection, we use a quadrature rule based on the vertices of the solid element, like in this case. And for the assembling with mesh intersection, we use the quadrature rule of order 3 in triangles, because the situation is this one, and we have to integrate Q2 times P1 function, so we need order 3 of accuracy for the quadrature rule in this case. Okay, we designed the preconditioner, and we can see basically the matrix of our linear system for the time-dependent case as divided into 4 blocks. The first one is the Navier-Stokes part, then we have the solid part, and A12 and A21 are the matrices with the coupling term. Okay. We designed 2 preconditioners. The first one is block diagonal. The preconditioner is the diagonal matrix, like here, and the block triangular, where the preconditioner is this triangular matrix. In both cases, the action of the preconditioner consists on the exact inversion of the 2 diagonal blocks, A11, A22, and as solvers, we use the GMRS for the linear system plus Newton method for the case of the nonlinear solid model. Okay, linear solid model. We consider the annulus, this annulus, defined by this way, placed at the center of a square, and basically we have that the annulus is stretched, and internal forces return it to its resting configuration. And thanks to the symmetry, we work only in a quarter of the domain. So we assume that our fluid domain is the unit square, and omega 0 s is also equal to b. So it's the resting configuration of the quarter of the annulus. This is the linear model to represent the solid behavior, and we assume that the 2 densities are equal to 1, and the viscosity is 0.1. Okay, this was a movie, but it doesn't work with Adobe. So basically, this is the quarter of the annulus that is stretched, and it wants to return basically to its resting configuration that is almost.
You can show it on the laptop.
From my laptop,
No,
it doesn't work.
the movie doesn't work.
The movie doesn't work. It's the reader of the PDF.
You have the file there, right?
Yeah, I have the file.
If you want to play the file.
I should have the files, yes. Well, we can try this. Okay, but you don't see it. Okay, nice. Berto, help me. Okay. So basically, this is the evolution of the system, okay? Optimality test, so robustness with respect to mesh refinement. We run this test with capital T, that is the last time instant equal to 2, with delta T 0.01 on 128 processors on sharing cluster in Chaos. This table is related to the coupling with mesh intersection. This second table is the coupling without mesh intersection. can see a couple of things, basically. The first one is that when we use the block diagonal preconditioner, basically in the case with the intersection, it doesn't work well. Okay. You can see here the number of iterations is almost 400, while for the block triangular, in the same case of the intersection, we have 16. While for the coupling without mesh intersection, we have 10 and 6. Okay. Other thing we have to observe is that the volume loss, that basically is the indicator in this case, because we don't know the analytical solutions, to see if the method works, basically. And we can see that the volume loss is better when we don't use mesh intersection. Okay. In the first part this morning, I show you that when you use the H1 scalar product for the coupling, if you don't use the intersection, it doesn't work. In this case, with the L2 scalar product, it works. This is a numerical evidence of this fact. We are working on a theoretical estimate, and it seems that basically when you use the L2 scalar product for the coupling, the method works and converges even if you don't use the intersection. Okay? So this is strong scalability. Okay, we look the speed up. Speed up, it means the factor when you double if you double, for example, the number of processors, you should have half of the time for getting the solution. Okay, in line with the previous slide, intersection and block diagonal, the result is poor, basically, because we have a speed up of 11 instead of the theoretical one that is, for example, 32 in this case, or 7 instead of 64. And this is better for the block triangular in the case of mesh intersection, because we have 49 instead of 64. That is, I mean, it's a good result. And the situation is different when we don't use the intersection. We can see a little bit of oscillation, we can say, because we have, for example, 56 instead of 16 and 55, so the same basically. Then we have 18 and 26 instead of 32. And then in the last case we have more than 200 and 300 instead of 64. So without mesh intersection we have this problem. It's not a problem, but I mean. Time evolution plots. So time evolution of linear iterations, CPU time to assemble the coupling term and to solve the linear system. This is related to a simulation with 32 processors on Shine, with this number of degrees of freedom and with the block triangular preconditioner. So with mesh intersection, we can see that, I mean, the linear iteration, independence of time, are not constant, like in the case of without mesh intersection. This is also due to the fact that when you use mesh intersection, the coupling term is more dense than the case without intersection. So probably the solver suffers, basically, solving this case, and the other results are basically in line with this fact. While in the case without mesh intersection, we have a constant number of linear iterations. Okay. And in terms of time to solve the linear system, okay, we can see the same for with intersection. Takes more than without. Volume loss, other thing. Linear solid model, solid mesh 384 times 192 on 64 processors. We can see that with intersection and with the block diagonal, basically the method doesn't work. While for the case with block triangular, yes, it works, and also with mesh intersection. The same if we use a coarse mesh for the solid. The problem probably is the ratio between h of the solid, the mesh size of the solid mesh with respect to the mesh size of the solid one. Okay. Now we move to the case of the non-linear solid model. We consider a bar immersed in some fluid. Okay, the fluid domain is still the unit square, and the domain B, that is also the resting configuration basically of the bar, is this rectangle. The motion of the structure is generated by a force that pulls down during the time interval 0, 1 in the midpoint of the right edge. I will show you the video. And this is the nonlinear solid model for the solid behavior. And W is the exponential strain energy function of anisotropic hyperelastic material. And we choose again rho f equal rho x equal to 1, and the viscosity is to be 0 point. The movie. Okay. Okay, so in 0, 1 we pull down the bar, and then it is released and it returns to the resting configuration. Okay. Optimality test, again with respect mesh refinement. First we have to notice that the block diagonal with the nonlinear solid model basically suffers, because, I mean, it is confirmed the result of the previous case with the mesh intersection, because it's basically the same, but without mesh intersection and with the nonlinear solid model, the block diagonal has also 3000 iterations, so basically it doesn't work. While in the case of block triangular, the method works well in both cases. Strong scalability, okay, we have the nonlinearity part, so the scalability suffers. We have 2 instead of 16 with mesh intersection, and 15 instead of 32. The volume loss, also in this case, is better when we don't use intersection, okay? This reason as before. Time evolution plots. Okay, I start from here, because in 0, 1, 0, 1 is the time interval when we pull down the structure, basically. So we can see that there is an increase of the CPU time to assemble the coupling term. Then when we release, it goes down, and the same is also related when we check the average linear iteration for nonlinear iteration and the CPU time to solve the nonlinear system. We can see that in 0, 1, the method needs to work more than in the case without with mesh intersection. And okay. Conclusion. Are there any questions about the parallels, or Umberto, tell me?
So you mentioned MAMS, right? Which is essentially an LU solver.
Yes. Okay, I don't know if I can answer to this question, because Simone Scacchi did the part about the preconditioner and I did the part about the coupling, but tell me.
Okay, so you mentioned the fact that you have to invert fully those A when 1, A when 2. So you mentioned, if you go back to your preconditioner, the way you precondition is that you create this block diagonal matrix in one case and you invert them exactly, and you do the same for the box diagonal. The exact inversion is what you use MAMS for.
Yes.
Okay. And then how do you deal with the sparsity loss that you have due to the fact that you're using an LU factorization?
I don't know, Umberto.
But you use MAMS there, so that's the reason why you mentioned MAMS.
Yes, we use the maps for the exact inversion. Yes, this is the point.
Yeah,
Probably also for this reason, sometimes we have that the method. I mean, these are two-dimensional problems, so they are not very complicated, you can say. And I don't know what happens if we go to the three-dimensional case with the problem of the exact inversion, because probably it will it needs more computational resources, I think.
But it means the value you want to convert them exactly.
Yes, exactly. This is, yes, exactly.
Like that.
Exactly.
Yeah, my question was related to this. I was wondering if you had to consider some inexact solves, such as these A1, A2.
Sorry?
If you had considered not solving them exactly, but inexactly.
Ah, okay. No, we focused only in this case with the exact inversion. We will see because we want to continue this research. So yes, probably we will investigate also this case.
And also a second question. So I was wondering, why don't you consider this alternative formulation that we've seen in your presentation? We have this 2-2 block, which is 0. I think you can rearrange this out for systems to block of the system.
Sorry, don't.
I think you can rearrange this out point system just that the 2-2 block of this big matrix is 0, right? Is that correct?
Sorry.
So,
I sono sordo, gente.
So you can rearrange it like in this format.
Yes. Double point.
Exactly.
Yes.
And once you have this matrix rearranged in this format, I think you can apply some standard.
Okay. Now I got the point. So you are telling me what happens if you rearrange the matrix? Okay, it's another thing that we should check.
Mhm.
Yes. The rearrangement of the variables as Najwa
I
showed.
think
Yeah.
it would be much better to actually consider this one.
Yes, probably yes.
That's the result of theory of numerical solvers for mixed problem.
Yeah.
Very rich.
How many physical cores has a single node on Shine cluster?
You know Umberto? No.
No, I don't remember.
We
Maybe
should.
the probability of scalability are related to hyperthreading.
Mm.
So everything it's okay up to 32 cores, and then you use hyperthreading and
No, but say that again, sorry. You mean it's up to 32 because you think you have 32 cores inside the unit?
physical cores are maybe 32.
No, I think it's
No, there are more than
more.
32.
The
Yeah.
core is more, and if you think that the bottleneck is the communication volume because you need to go
Yeah.
from one stack to the other, might
Okay, I mean, if you increase the number of processors, I mean, you have at the time where,
Yeah, but these tests are on a single node, right?
yes, single node.
Okay.
So no, it's more for sure the number of physical cores that you have per node. If I remember correctly, it was an odd none in the order of 30 because I remember the presentation of somebody.
Mm. But for sure they are more than this.
32.
So if there aren't any other questions, I do like the summary. If you're still alive. I'm not. But so starting from this morning, we discuss the immersed boundary method formulation and how we moved from the immersed boundary to the fictitious domain with distributed Lagrange multiplier. Then we discussed the time semi-discretization, the analysis of the stationary problem. Then we moved to the simple case of the elliptic interface problem. We discussed the assembly of interface matrix. Najwa discussed new elements for discontinuous distributed Lagrange multiplier and posteriori error analysis for interface problem. And then we discussed parallel solver. As we say in Saudi Arabia, finished. And